Hello, this video is one of three on chapter 3, allocation of one input, variable input. The second video will present building graph using Excel for the new functions we are discussing in this chapter. And the last video, the third one, will be about a practical example. We built two simple models earlier. We discussed the production function and the cost function. In this chapter, we'll put both together to talk about the profit function and optimum profit. We need to set up a few conditions for our model to be viable. The necessary conditions assumes that the producer uses the best production process that exists and at an optimum level. So basically, it will not be possible for anybody else to do better. It's a strong assumption, of course. The second assumption, also very strong, is the assumption that of the necessary conditions, like a condition that we are operating in a perfectly competitive market, both for input and output. In the real world, obviously, perfectly competitive market describes pretty well agriculture world or agriculture market. However, obviously for input, especially is different. Large commercial farms who buy large amount of input are likely to have lower prices per unit than small farmers. The second sufficient condition, that's how we call it, ensures that the producer is optimizing her objective regardless of what it is. And so we talk about the different objectives that can be optimum. And the objective can be to maximize yield. It can also be to maintain the quality of the soil. It could also be to use the minimum input possible, right? And so the objectives can be, will vary. In this chapter, we'll assume that the objective function is profit maximization. We'll be first using the total value product and the production and the profit function to find out the minimum or the optimum input that will be used to maximize profit. And if we talk about profits, we obviously talk about the key variable, which is price, that we did not use before. And so one concept that we are introducing here too with price, okay, is the total value product. The total value product is nothing but the total revenue, okay? We use the term total value product simply because it's in accordance with what we really want to try to define. And most importantly, the total value product explicitly embodies the concept of price and output. So this is our profit function, is pi. Okay, so we often use pi. If it's in pi, that you know from algebra or geometry, we also use pi to call, okay, to represent the profit. So of course, profit is revenue minus cost, and we break it down. Okay? And we are breaking down because we are trying to find what the optimum X is, the optimum input. Okay, and so to do that, we need to derive profit as a function of input. So the Y that we have here, we output here, we'll define it as a function of output. And we know that Y is a function of input. So that's what we do, and everything else remains the same. And so the derivative, okay, and so the derivative of Y with respect to X is, as we know, the marginal physical product. And so when we come here, when we derive profit, it's price of Y, this is PY, this is PX, okay? So the derivative of profit with respect to X, so is, of course, PY does not change, okay? Time the derivative of Y with respect to X, okay? This is what our Y is. And since we are deriving respect to X, minus PX, okay? The total cost is a value, a number, is not a variable, and so it does not appear in our derivatives. To optimize, we know that we set the first derivative to be equal to 0 because the first derivative represents the slope of the profit function. And so that's what we have here. We have PY time, as I showed earlier, it's time marginal physical product minus PX, and those are all X's. I change them over time and they come back to capital X's. I don't know why. Okay, and so this gives us that's value marginal product, okay, because PY time marginal physical product is, we call that value marginal product, as I talk about, we call it value marginal product, equals PX. And so this is the condition for profit, for input optimization. And value production, value marginal product is nothing but the value of the output being produced, of additional output being produced, because value marginal product is the price of the output times the marginal product, the marginal physical product, okay? And so is the value of an additional output being produced. And of course, for the farmer to produce an additional output, she needs to use inputs that are not more expensive. Okay, the amount of input that needs to be used should not be higher or more expensive than the value of the output. It can be cheaper, that results in additional profit, but it cannot be higher. Otherwise, of course, you are producing something that is value 10 and is costing you 12. Obviously, you are not going to do that. So that's what I was talking about earlier, right? The slope. So this, as we found out, right, is the slope of the total value product or total revenue. Okay, that's our result because it is a derivative, and it's called value marginal product. And PX is the slope of a cost function. So we can see that Px being a value 2, right, is the price of input is fixed because we're in perfectly competitive market. That price of input does not change, it does not vary. So it's a fixed value. And so its derivative is going to be 0, right? It's going to be a straight line. And we'll see that later in the graphs. So we have two different slope, right? That's of a total value function, and that's of a cost function. So obviously the objectives is, yeah, sorry. All right. So this reproduction again of the textbook table. And so I drew the total value product function. This is the total cost function. And this is the profit function. Okay. So what we are trying to figure out is the highest point, okay, zero slope on the profit function. And knowing that it's the same slope as the price, so this is Px is vertical, right? So profit will be optimum or maximum at this level here, and we can determine exactly what the number is, and we will do that. And of course, it will be at the point where the value marginal product equals the price of input. Okay. If the producer want to increase output, because this is dollar value, and these are this line are outputs, Y and Y. Okay, our line here is output. If a producer say, well, I want to maximize profit because profit is maximum here, you know. So at the sorry, output, at the output maximum, okay, 20. At the maximum output, so actually it's 20, but my 20 is approximately here. Okay. Normally. At the maximum output, because I'm following this line of maximum output. Change color. Okay. So, well, okay. I'm taking this line here in blue, I'm drawing it. And so if the objective is to maximize output, the highest level output will be here. Okay. But at this level here, we can see that the price is higher than the value marginal product. And so that's mean that if price is, in our example, 100, at this level, okay, value marginal product is below 100, right? Okay, value marginal product is below 100, and let's say that is 80. And obviously you don't want to be here. And so what you can see is that maximizing output results in loss. Okay, so the maximum in output is not the same as the optimum profit. And that's what we see here on this graph. Okay. So algebraic representations are production functions. Oh, sorry, this stuff here. It's messing up. Eraser. Erase those things because they show up on the next slide. And I don't want that. Okay. So, so this is an example of production function, y. Okay. And so if you derive that production function, we get this result here. This is still not going away. We got these results of the derivative of the production function. And so, of course, we set the derivative to equal 0. We're looking for this condition here, where price times marginal product equals price. Okay, that is optimum optimization function. And that's for the profit function, right? Okay. The profit optimization condition is this one. So marginal physical product is what we just computed, okay, and is equal to the price of input px, which is 100. See how it works? Okay. All what we need is a production function, the inputs and output prices. And once we have the marginal physical product, we derive and apply the optimization condition for profit. Okay. And so we just replace our px, marginal physical product, and output price, py and px in our function. So that gives us, it's not clear, but it gives us ultimately this function here that I'm circling. Okay. So this is what the x, we want to derive x from this function. Okay, what is the optimum x from this function? And so we have a quadratic function, which is 0.1 x squared minus 2x plus 10 divided by 3. 10 divided by 3, of course, we take the 30 here and we move it to the other side, right? We move the 30 to the other side here. And so it's 30 divided by 100 is 3 divided by 10, or 10 divided by, so 100 divided by 30, which is 10 divided by 3. And so to get the optimum of this quadratic function, we apply the quadratic function formula. And by applying this formula, we found that the optimum profit is obtained, okay, when output, the quantity of output use is, input use, sorry, is 18.2. So here, so I have y, I have x. This is, no, sorry, x. And this is y. I think I made a mistake earlier. Yes. So this is x because it's inputs. We are deriving with respect to x. And so this is x. Okay. We have y when we are deriving with respect to y, right? But here we are deriving with respect to x, so we have x there. So our value here, our line here, this represents x's. And so what we are saying here is that the value marginal product, okay, it's the producer's demand curve for input. What does that mean is that as we are adding input, okay, something else is happening. As we are adding input from left to right, okay, we are increasing input. We had the output, the corresponding output. So you get to maximum here, but then as long as the value marginal product is above the input price, so this price is px, okay, then you can continue to apply input because the difference between the two is profit in any case. You stop when the quantity of input you are using, okay, its price is equal to the value marginal product. And that is the condition that we have, value marginal product equal px, okay? And so the value marginal product is the input demand function for the producer. Here, we use the same procedure to find the optimum amount of output. So to do that, what we need to do is, so this is on the right here, okay? This is the profit function that we set up earlier, and it was py as a function for fx. Here, because we are trying to find the optimum y, okay, we'll set up the profit function the same way, but the difference is that we are going to replace this x function, right? To make x equals is a inverse of y. We know that already, okay? We discussed that earlier. The f function is the inverse of y. So the derivative of dx with respect of dy, okay, we can see that this is the inverse of the marginal physical product. So when we are deriving this function here, okay, is with respect to y, so is py minus px times the derivative of the function, which is dx divided by dy. And so if we continue working on this, we have our same py, okay? As I showed you earlier, this is the inverse, the derivative is the inverse. And so we have px times the inverse of the marginal physical product is equal 0. So this becomes this becomes the output maximization function. So ultimately, what we have is the derivative of profit is going to be the derivative of total revenue minus, of course, the derivative of total cost. And this function will have, this is py minus px, or py equals, okay, px times 1 over marginal physical product. Okay, and it's not here. We can easily show that 1 over marginal physical product is actually the marginal cost. And so what we are trying to figure out is price of y equals px times marginal cost, right? And so this is basically the inverse of what we found here. So what we're trying to find out is, given the output price, okay, the input price, that the input value that we need to use cannot exceed the output price. Otherwise, again, we'll be losing money. Okay, and we can call this, of course, value marginal cost. Is the value of the input has to be equal to the price of the value of the output. Okay, so it's very, very logical. And so obviously the two methods are very comparable, and those are basically the two result that we have ultimately, right? Actually, is this one, value marginal product equals px, and then we found x, and the other one is marginal cost. Actually, is marginal cost. This represents the marginal cost. Sorry, marginal cost equals price of output. Okay, so those are the two conditions, and we'll take, even one more video will take a practical example and apply all those concept again with in application. Okay, so I will see you next time.